resistant to change, that means I don't want to change. And Newton's first law says that an object at rest is going to stay at rest. Alright, so if I had a rock and it's not moving, this is a rock, right? What's going to happen to the rock? Will it move? Will it move? If there's nothing to move it, will it move?
No.
Because an object at rest will stay at rest, right?
Yes,
What will make it move? Wind or another force, right? So an object at rest will stay at rest unless something, an unbalanced force, causes it to move, right?
Yes.
Now, it also, the next part to Newton's law, it has two parts. An object in motion stays in motion. What does that mean? Okay, so if I throw this pen, right, this marker, what's going to happen to it? It's going to move, right? And it's going to keep on moving, right?
Yes.
It's going to keep on moving. But what happened? Why did it stop?
It hit another force.
It hit another force, friction. All right? So a ball that's moving. Y'all see my moving? All right? A ball that's moving is going to keep on moving until. So if I roll this, is it going to keep on rolling?
No. Until another force acts on it.
What's going to act on this? It doesn't hit a wall.
Friction.
Friction. What is friction?
Something that a force that slows down an object.
The
Okay,
resistance of like the air.
Right. All right. So there are different types of friction. I want y'all to know that friction is a type of resistance that acts opposite to the motion. So if the motion is going this way, friction is moving in the opposite direction. And eventually it's going to slow something down or stop it completely. All right? So there are different types of friction. So the floor exerted rolling friction. There is static friction, meaning that wall, this wall right here, has static friction. Because if I push it, it's not going to move. That's static friction. The rolling friction is when I roll this, there's friction acting as it rolls. There's also something called air resistance. That's a type of friction. Y'all have seen cars race before, right?
Yeah.
When the cars race, like a drag race, right? If they want to stop, how do they stop? They slam on the brakes. Are the brakes enough?
No. What about a tire?
What do? These little speed cars, they look like this, right? With a little spoiler, right? They drift, and when they want to stop, they execute a little parachute. Y'all never see them do that?
No.
Are you serious? Y'all never saw a car with a parachute?
No.
Yes. In movies. In movies.
Y'all see the parachute?
Yes.
All right. When they want to stop, they have to slow down real fast because it's a short runway. So in order to slow down, they deploy parachutes. So the parachutes catch the air, and the air creates friction, and it slows the car down. That's how planes stop when they land on the runway. All right. They have little parts on the wings that they drop in order to create more drag.
I was looking what those things do.
All right. Yeah, it's a different type of road, and they use different type of tires too. The tires are stickier and they're smooth. They're not like the tires with the little grooves. They're basically smooth tires, and they're sticky because they're going so fast. All right, and they're smooth so that they have as much friction to slow them down. But if your tires don't have grooves on them, it's like if your shoe doesn't have ridges,
It's got
what
an
happens when you're
brake.
trying to stop? If you're running,
No friction is gonna
there's
act
no
on you.
friction, so you're gonna what? Slide. That's why they have to use the little parachutes. All right.
Those are cool.
All right. So this parachute creates air resistance. Does anybody know what's the other word for air resistance? It's the name of the race.
Drag?
Drag.
Yes.
Drag is the word for air resistance. All right. All this to say, Newton's first law: an object at rest stays at rest. An object in motion stays in motion unless it's acted upon by an unbalanced force. Everybody gets that? So this will stay exactly where it is until something moves it, acts on it. This will keep on rolling until something acts on it. All right. So everybody understands the first law?
Yes.
All right. Newton's second law. Newton's second law is a formula. F equals ma.
What does the M stand for, you guys think?
Mass.
And what about A?
Acceleration.
And then F?
Force.
Force. Awesome.
Let's learn Newton's second law of motion. Newton's second law of motion. Before understanding Newton's second law, you must know about acceleration. It is the rate of change in the velocity of an object. The second law of motion states that the greater the mass of an object, the more force it will take to accelerate the object. There is an equation. Force equals mass times acceleration, or you can say F equals m into A, where F is the force and its unit is Newton. M is the mass and has the unit kilogram, and A is the acceleration, which has the unit meters per second squared. In simple language, Newton's second law states how fast an object can move. This also means that the harder you kick a ball, the farther it will go. Oh, it seems you are not understanding this. Your friend is on a skateboard. You push him forward and he begins to move slowly. Now, a big push, and see, he moves faster and gains speed much faster. Now your friend gets in his car. You push the car, but it is so hard to move. You pushed harder, and it barely begins to move. Oh, and now you are pushing it with some other friends. See, it moves faster and faster.
What is the formula for Newton's second law?
F equals ma.
All right, Newton's second law states that force is equal to mass times acceleration. What would the triangle be for this?
F
Where does the F go?
on the top.
On the
On
top.
the top, okay. And where does the M
On
and
the
the A
left.
go?
On the left.
And the A's on the right.
All right. How do we know our equation is correct? By checking it. How? What do we have to do?
Look at the phone.
We cover up what? F, right? Because that's what they gave us. If we cover up F, is it M times A?
Yes.
All right, so we know that this formula matches up with our triangle and we put everything in the correct place, right?
Yes.
All right. So Newton's second law is a formula. It says that if we increase the force, if we keep the mass the same, what would happen to our acceleration? Think of it as pushing, right? If I push this a little bit, it's going to roll a little bit, right? If I increase the force, what's going to happen to the acceleration?
Going to move faster.
It's going to move faster. So if I increase force, I'm going to increase the acceleration. All right, what about if we change the mass?
Decrease the acceleration.
if we increase and we keep acceleration the same, all right? If we increase the mass, if we want to keep acceleration the same, we would have to do what with our force? All right, think of it as a grocery cart. All right, we have a grocery cart that's empty, and then we have a grocery cart that is full. All right, now, what will we have to do if we want to push them the same distance?
Add more.
Add more force. So we have to, if the mass increases, we need to
Add more force.
increase our force. Y'all give it, it's pretty much, if you think about it, right? If the mass increases, if I want to move it, I'm going to have to put more force. So when y'all see these things, don't think of them as just this weird math formula. Apply them to like real life. Math. If something is heavy, if I wanted to move, accelerate, what would I have to do?
Push it.
Add a force, right? Push it harder. Y'all get what I'm saying? Yes.
No, I don't understand.
This one. All right, and then we have Newton's third law. Newton's third law states that for every action, there's an equal and opposite reaction. And it's kind of hard for us to imagine that. So think of it as riding on a skateboard. Has everybody ever used a skateboard before?
No.
I don't hear anything.
No one has ever used a skateboard?
Not
Alright.
the proper way.
Okay, I don't know what that means. But if you get on a skateboard, if I want to go forward, which direction do I need to push? Can I push forward to go forward?
Push back.
Why can't I push forward to go forward?
You propel yourself backward.
Right, because for every action, there's an equal and opposite reaction. So if I want to go forward, I have to kick backward. That's the opposite reaction, so I can get a forward direction. Everybody gets this? Yeah. Kanaya, did you get that? All right, now, it's easy to see in space. Because in space, there's nothing, right? They're just floating around and on these, what do they call it, space stations, right? So in order for them to move from one point to the other, if I'm just floating in the air, how do I get to move forward? If I'm just floating right now in the air, how do I move this way? Can I just walk? There is no floor for me to push. So in order to move forward, what do I have to do? I have to like throw something or push off on something. So what happens is, if you have something, you would have to like throw it. And it was in the movie Gravity, which we gotta watch. Where if she wanted to move, all right. So he's gonna demonstrate
Welcome to the International Space Station. I'm NASA astronaut Mark Vandehei. Today, we're going to talk about Newton's third law. How do you think it will hold up in microgravity?
For every action, there is an equal and opposite reaction. This means that in every interaction between two objects, there are a pair of opposite forces acting on each object at the same time. A force pair. You can see that there are many examples on Earth.
In order for us for the car to go forward, we have to push
our body
backward.
In
You're looking
space,
at different
thrusters expel
action
one way, and the
reaction.
vehicle is steered in the opposite way.
Well, again, more basketball stunts that I can't do on the ground. At least not while getting this much hang time. All right, back to serious business. Got a basketball right here. Going to be object 1 on the second object.
Close as you
If
can.
object 2, myself, applies a force to object 1, then that same force will be applied according to Newton's third law by object 1 onto object 2. However, there's a big disparity in the mass. Object 1 is a very light mass object. Object 2, myself, is a larger mass object. So, I'm going to try to make myself about the same shape as this ball. See how that works for us. And I'm going to apply that force. You saw that force applied to the ball made it accelerate quite a bit. It really didn't accelerate me much at all. Newton's third law again, but this time we're going to use two similarly massed objects. Joe and I have about the same mass. So Joe, get into a ball. I'll do the same. I'm going to face you this way so that I don't throw you into something you can't see. Now I'm going to get into a ball behind Joe, and I'm going to apply a force to him.
What should happen?
Whoa!
They can hurt themselves.
Notice that when I apply the force to Joe, it accelerated Joe away from me, but I got accelerated away from him as well, because the force applied to Joe ended up being the same force that was applied to me. Now you've seen Newton's third law in space. Now test it out on Earth. See you next time.
That's probably cool. All right, so everybody got Newton's 3 laws.